We're going to start on chapter 6 today, which is basically adds in a few new concepts, teaches us a little bit more about circular motion in terms of forces. And we learn a little bit about friction. So, I'm going to take this book right here. Sorry, my top just keeps nagging me, so I hope it doesn't bother you. But okay, so if I look at this book for a moment, I slide it across here, it comes to rest. It comes to rest because of frictional forces. Now, I'm also pushing on this right now. I'm pushing on this book, but it's not moving. We know that is friction. So there's something called static friction and there's something called kinetic friction. Static friction means statics, for example, something that you will study later, especially during the years. Statics means it's not moving. Static is stationary. Kinetic just means that it's moving. So if I put this right here and I start exerting the force onto that, but it's still not moving. What's happening here? And I can vary the strength of this, right? I'm pushing harder now. I'm right now progressively pushing harder and harder and harder and harder and harder, and now it starts moving. What's happening? Yeah. Okay, so now this is an important and a little bit of a subtle point, and you're right on. So what he's saying is this static friction is the opposing force to me applying that because it's not moving. But the static force, yes?
Static friction actually is the force that you're dealing with equal to
Okay, good. So static friction actually increases with the, as the harder I push and it's still not moving, that static friction is increasing, right? So that the net force is 0. There is a maximum static friction that you can have, at which you overcome the static friction and it starts with kinetic friction. Okay. If I'm riding in my car and this is a classic weather for it, and I slam on the brakes, what happens? And let's say I'm on an icy road. Start sliding. What is the optimal method for stopping a car on a slippery surface, for example? You want to go to the position of maximum static friction. That's why some of your cars have what's called traction control system, or that prevents the car from sliding friction, because the coefficient of static friction is higher than the coefficient of kinetic friction. Now with static friction, that means, now you normally think, well, you're moving with your car, right? Your wheels are turning around, so why would that be static friction? Why would you want your wheels to be able to rotate while it's moving, rather than having them put on the brakes so that they seize and start sliding? Yes? Okay, so when the wheel is rotating, at any one point, if you look at that wheel rotating here, it is static. It's as it moves, as this wheel is moving around, and you look at any one point on that tire, and its interface with the road, it's actually a static friction. But when I seize the brakes and it starts moving along like this, so that the tire, now that one point is sliding across the ground, that's kinetic friction. But as it's rolling, and I look at any one point on that tire, as it rolls along with the road, then it is undergoing static friction. So you want to be able to take your car, have the tires rotate, but you want to go to the maximum static friction. That's why slamming on your brakes is a bad thing in these sorts of situations, although that's what we're trained to think in emergency types of situations to just slam on the brakes. So that's why a lot of these new cars have the ability to go to the position of maximum static friction. And you'll often hear it. If you're sliding, you'll hear your car. That's just basically a way of regulating the brakes with the maximum static friction. So, some key important things. Static friction increases proportional to the amount that I push on it until finally it starts to move, and then it's considered kinetic friction. So what we're interested in this course will be often what is the maximum static friction that I can have. Okay, so we'll refer to this as FS max. And then we're interested in looking at the coefficients of this kinetic friction. And as we know, friction always opposes the direction of motion. Okay? Questions? All right, let's put a few equations to this. So, we're going to refer to this as the static friction maximum is equal to mu s times the normal force. Fk is the friction for the kinetic. We don't worry about whether it's maximum. We're just going to assume that Fk is constant. As long as it's sliding, this is the coefficient of kinetic friction. Okay? So this is going to be F, which is mu k Fn. Or this is the normal force. Is this a vector relation? Are these vectors? Okay, now I know that the normal force is a vector, but this is not a vector relation, and I'll tell you why. Because this is always in the direction that opposes motion, and this is in the direction that's perpendicular to the slope at which the object is sliding on. So we have to be very careful. This is not a vector relation because you can't say the vector here is proportional to this, because they would be in two different directions. Okay? This is always opposing the direction of motion. This is perpendicular to the surface. Okay, so we don't write this out as a vector. This is simply just a relationship between the frictional force and the normal force. So let's do a couple of examples, or what are a couple of things? So for example, an egg on Teflon. Any ideas of what the coefficient of friction would be on that? You all have Teflon pans, right? You put an egg on it, boil it. Would you want a large coefficient of static friction for your egg on a Teflon pan? No. What do you expect it's going to be? Small. Turns out that an egg on Teflon is I think it's about 0.04, and this is mu s. Okay. Now mu s, for example, then one of the things they talk about in the book is, for example, rock climbing shoes on rocks. Now that would be a situation where you want a very high static friction, and that can be as high as 1.2. And one of the things that's very interesting in car racing is they want tires that can give you the maximum amount of static friction. Right? So I believe, I don't know exactly how high it is, but they can get much, much higher than 1. I don't know exactly what those numbers are, but there's a lot of engineering that goes into manufacturing tires. Okay. Now, so just as a reminder, this we're going to assume is the maximum static friction that you can get, and this does not depend on speed. Okay? So when something's moving, we're going to assume no matter what that it has mu k the whole time. But as we've also pointed out, the static frictional force can be proportional to how much you push on it until it starts moving. Okay, so let's do an example here. Okay, so one of the examples that they show in the book is you have a brick sliding along a surface. There's an applied force here, which we call F, and it's angled at 30 degrees down relative to the horizontal. Okay, so let's label all the forces that we have in this free body diagram. What other forces do we have? Sorry? Okay, we have gravity. What else do we have? Sorry? Normal force. Okay, do we have anything else? Sorry? Okay, we have frictional force. Good. So now, what we're going to do is we're going to say, so we've drawn our free body diagram, we've looked at all the forces, and now we ask, what is the optimal set of axes that we want to use? Well, the optimal set of axes in this case are just going to be parallel to the surface here. And now we need to break it up into components. And let me just draw these as vectors here. So let's first look at all the forces. So let me also say one more thing. The mass of this brick is 8 kilograms, quite a heavy brick. So what we want to know is this force that's being applied to this brick sufficient to move the brick? What way should we attack this? Yes? Okay, so let's first find, as was pointed out, let's find out what the force is that is being put in this particular direction. Okay, so how do we do that? Well, we just simply take the sum of the forces along the x direction is equal to this F cosine of 30 degrees minus F. Now, do we know? We don't know if this is accelerated or not, right? So what we need to do is first find out what is this. Okay? This is what was being pointed out. So if I say that this is so F is equal to 12 newtons here. That's the magnitude of this applied force. And so if I take F cosine of 30 degrees, that's equal to 12 newtons times the cosine of 30 degrees, which is 10.4 newtons. Okay, so we see that this is the amount of force going this way. Now, let's find this, the frictional force. How do we do that? Okay, so we need to find first we need to find the normal force, and then we multiply by the static friction. So in this particular case, what they've given is that mu s is 0.7 and mu k is 0.4. So we want to see what we have. So let's do the sum of the forces in the y direction. So if I take the sum of the forces in the y direction, I have F normal minus F gravity minus F times the sine of 30 degrees. Okay? So I see that this is F normal minus mg minus the F sine of 30 that's equal to 0, right? Since it's on a surface, it's not accelerating up or down, and so we say that this is equal to 0. From this, we can see that F normal is therefore going to be equal to mg plus F sine 30 degrees. Okay, so this is 8 kilograms times g, which we'll say roughly is 10. Right? And so we have to say 10. So we have 80 newtons plus F sine 30. I remember exactly. Sorry? Oh, right. Okay, good. So that's, let's say it's about 86 newtons. Sine of 30 is half, right? Okay, good. So we have sine of 30, so this is roughly 86 newtons just based upon these. It's actually a little bit less than this because this is actually 9.8. But anyway, so we have 86 newtons. Now, what is the frictional force going to be? What is the maximum static friction force that we can have? Well, it's going to be 0.7. I think they said 0.7 in the book. I think it's 0.7 or 0.7. But you have 0.7 times 86 newtons. And that's in the neighborhood of say, 50, right? So is that going to be, like 56? So is that greater than 10.4? Yes. So therefore, is it going to move? No, it's not going to move. That means that this coefficient of friction, or this frictional force, is greater than the applied force in the horizontal direction, and so it will not move. Okay? So what is half of F now? Okay, we try. This isn't moving, right? It's negative 10.4. Because now that we know that this is not moving, we replace this question mark with, we know that this is the maximum force that we can have is much, much greater than 10.4, and so therefore it's not accelerating because the friction would make it go backwards, right? So we're assuming that it's not accelerating, and so therefore we have this equation now, and so we can see that the frictional force is going to be equal to F cosine 30, which we determined earlier was 10.4 newtons. Okay? So the frictional force is 10.4 newtons. Questions? Okay, great. Thank you. So now let's do an interesting problem, which is a car moving on 3 types of surfaces. The first one is going to be just a regular dry road. The second one is going to be an icy road where we change the kinetic friction. And the next one is going to be an icy road at a slant, an icy hill at a slant, and also with the same kinetic friction as what we get on the flat road. So we're going to do 3 things. We're going to assume that this velocity initial is 10 meters per second. I think is about 21 miles per hour. So we're not going too very fast. And we're going to assume in case 1 that mu k, well, we can just assume 0.6, I think is what they said in the book. The second one, mu k, is equal to 0.1, and the third one is mu k is equal to 0.1, but at 5-degree slope. Okay, so we're going to assume that this car is first flat with a high coefficient of, with a relatively large coefficient of kinetic friction. Then we're going to reduce the kinetic friction because we're on a slippery surface. Then we're going to keep that reduced kinetic friction, and then consider what happens when we're on a slope. And it's pretty dramatic what happens in these situations. Okay, so let's do case 1 here. Let's draw the free body diagram for this. What are the forces acting on it? Okay, we have gravity. Okay. We have the normal force. We have force of friction. Anything else? So all we're going to assume is that this is going at 10 meters per second, and then suddenly someone slams on the brakes, and we want to see how far this car slides after slamming on the brakes. Okay, until it comes to rest. So what's the final velocity? V final is equal to 0. Okay, so now we're going to need to find sum of the forces in the x direction is equal to Ff is equal to max. Okay? So there's only one force in the direction of this car, and because of how we've defined the axes, we're going to assume this is negative, as a negative frictional force, and because of that, it's going to also be negative here for AX. So that just tells us the magnitude of this acceleration for this system. So all of the acceleration is due only to this frictional force. Now the sum of the forces in the y. We need to find out what the sum of the forces in the y is so that we can then go back and determine what the frictional force is. So we have F normal minus mg is equal to 0. So we see that Fn is equal to mg. We put that back up into here. And so we see that A, so now we have Fn is equal to this. And so we can find out what F frictional force is here. So we use this. That, and I'm just going to drop the minus sign for both sides just because I have minus on both sides. So just remember that the acceleration is in the negative direction. Well, okay, never mind. Okay, so now we have mu k times mg is equal to max. Okay? I should say here, when I say that F is equal to ma, I can just say that this is minus F, and this tells me that the acceleration is in the negative direction. I should be a little careful of that. But because this is negative, this just shows me that the acceleration is in this direction. But anyway, as long as we keep track of that, it doesn't, as long as we remember that A is in a particular direction, that's what that is. Okay, so now we see that the masses cancel out, and so we see that Ax is equal to mu k g all over, oh, sorry. That's always all right, so with that in mind, this gives us the maximum deceleration that we can have, which is going to be 9.8 times whatever this coefficient of kinetic friction is. And so if we assume this is 10, we'll just assume that Ax is equal to minus 6 meters per second squared. Just pointing the direction that it's accelerating. So now how are we going to find out how far it moved before it comes to rest? Well, there's one very good equation, right, which is x final minus x initial. Now, if we just look at that, that's the distance right there that it moves, because we're going to assume that x final is some value, and x initial we can just say is 0, right? Is equal to v squared minus v0 squared all over 2ax. So, this particular case, v squared is equal to 0, right? 0 minus, so this would be 100 meters squared per second squared, right? Because this is my initial velocity that I'm traveling at. And then we have divided by 2 all over 6 meters per second squared. Okay, so what does this give us? 100 divided by 12. Okay, good. So it's a little bit more than 8, right? 8 times 12 is 96. Do half again, 8. So we get, this is a little bit more than 8. So, oh, sorry, 8.3 meters. Okay? Oh, sorry, forgot to put the numbers in there. So it moves a total distance of 8.3 meters before it comes to rest. Okay, so now let's do the next situation. Now the next situation, all that we have is instead of coefficient of kinetic friction of 0.6, we have a coefficient of kinetic friction of 0.1. So instead of getting minus 6 meters per second squared, what do we get? Okay, so instead of 6 meters per minus 6 meters per second squared, we get about minus 1 meter per second squared. Right? And so now we're going to get roughly, so we get minus 100 meters squared per second squared over 2, which is about what? 50 meters. So it's only going 10 meters per second, but it takes 50 meters to stop. Okay, that's a pretty dramatic difference. So all we did in this case is we said A of x is equal to mu kg. If now mu k is just 0.1, I get 0.1 times 10. I just get 1 meter per second squared. And that I plug that back in down to here, and I find that the distance is about 50 meters. That just means approximately 50 meters to stop. Okay. Pretty dramatic. Now, case 3 is a little bit harder. Because now we have to rewrite all of our equations because we're going down a slope. So here's the situation. We have a car coming down here on a 5-degree slope. And we need to be able to, I'm just going to draw this as a box. So now we have to do things differently. We have to label everything so now I have its mass, gravity, mg, coming down. I have the force of friction going up, and I have a component going downwards. Now, why is this going to affect the outcome? Why will this change it dramatically relative to this? There are 2 reasons. Yes? is that the normal force is now reduced because it's at a slope, right? So the frictional force is reduced. What else? There's also another reason why this is a bad situation. Yes? Okay, so now we also have a component of gravity that's going in opposition to the force of friction. Okay, so we need to be able to write this in terms of its components. So if I draw my free body diagram, I choose my axes, and I say that my sum of the forces, and I'm going to assume this is now my new x direction, the sum of my forces in the x direction, I'm going to have an mg sine theta minus force of friction is equal to max, and the sum of the forces in the y direction, I get F normal, the normal force, minus mg cosine of theta, and that's equal to 0. Okay, so now I need to take this result and plug it back up into here, right? Because I have F normal, and so I can see that this, if I take this and apply it back up into here, because it's just going to be the coefficient of kinetic friction times mg, so I get the coefficient of kinetic friction times mg cosine theta. So I get mg sine theta minus mu k mg cosine theta is equal to max. Okay, we see that the masses cancel, and ax is equal to g sine theta minus g cosine of theta. G UK cosine theta. Anyone have a calculator on hand? Okay, I can just look in the book and see what those numbers are. But okay, in the end, it gives this value right here as being minus 0.1. Okay, so we're going to do minus 0.122 meters per second squared. So this almost counterbalances this, right? To the point that if it was any steeper, it wouldn't stop. That's kind of a scary thought, right? So if you do this, now how far does it slide? So if you remember, it was 1 meter per second squared on flat with mu k being 0.1, mu k being 0.1, and now at 5 degrees, it's about 8 times smaller still. Okay, so whatever this is, we multiply by roughly 8, so we have about 400 meters before this thing comes to rest. So going down a 5-degree slope, actually, with the same UK as on the flat, it took 8 times further distance, it took 400 meters for this to stop, which is a pretty incredible result. And if this has probably been 6 degrees, my guess is it would be that it would just slide almost indefinitely. Questions? No? All right. So let's do drag force and terminal speed. Who's ever skydived? Anyone skydives in here? Okay, who can tell us what terminal velocity is? Okay. Did you hit terminal velocity when you skydived? Where you go and you're just moving at a constant speed? Okay. Okay. Anyone know what terminal velocity is? Yeah.
Isn't it the maximum point to which the force of gravity and air resistance cancel one another out to a very constant rate?
Yes, that's right. So what happens is when you skydive, right, initially you just start falling. You've all seen those movies where someone's falling like this versus when they go like this, right? When they do a dive. So apparently there's one cool story in the book about this woman, and there were a group of people skydiving, and a woman had bumped into someone in the skydiving process and got unconscious. And she was just in free fall, and another person did a tuck where he put his body into a straight nosedive and then came out of it like that and was able to pull her chute so that she could survive the fall. So anyway, and there was only a few seconds before he didn't go. Anyway, it's pretty intense. Must have been a pretty intense story, but apparently he was able to get up to almost 400 kilometers per hour. Oh no, 320 kilometers per hour by doing this. And that's simply because when you're like this, you have more cross. You know, if you're falling like this versus falling like this, you have more cross section. How many of you like to bike road race? Right. So why do you bike in groups?
Because when you're biking behind someone, you have to do deep gear,
Okay, you get to draw on their drag, right? You get they're basically going through the wind, and then you can use that to reduce your. Well, they actually have curls around that, and that actually can help push you along, right? And that's one of the reasons why birds fly in V's, right? You're reducing the instead of cutting through the wind initially for yourself, they've already done it, and that causes currents and stuff that you can reduce your drag when you're going through. So now, so if at terminal speed, you've probably all seen it if you've tossed a rock off a large cliff, that it will accelerate for quite a while, and then it will just kind of hit a. It depends on what the rock looks like, right? The big flat rock you can throw up, and it will stop going. It'll stop accelerating and just kind of go at a constant speed. Anyway, this is terminal velocity. It's basically when a terminal velocity is the velocity at which we'll just call this drag, at which your drag is equal to your gravitational force. Okay, and we're gonna say d, its magnitude is 1/2 c rho a v t squared. And what I mean by here is this is drag terminal. So this is the drag force for at terminal velocity. And what this is just a coefficient that depends on whatever the, it depends, it doesn't vary much, as the book says, for example, between, say, 0.4 and 1. But it depends on a little bit of what is passing through a particular object. And the rho is the density of the air that you're passing through. This is the cross-sectional area. And this is just the terminal velocity. So let's look at this for a moment and figure out what the terminal velocity for a skydiver is, or the speed at which the person is falling, where the air drag resistance is equal to the force of gravity. So I have 1/2 c rho a vt squared is equal to mg. So let's solve here for terminal velocity. Terminal velocity is therefore going to be equal to 2 mg all over c rho a, and take the square root. Now let's just do some numbers. You're a skydiver. Let's just do some simple numbers here. Suppose the person is 100 kilograms. So I have 2 times 100 kilograms times, I'm just going to say 10 meters per second squared, divided by c. And now we're just going to use a number between 0.5 and 1. So let's just assume it's 1 for simplicity. And then the density of air. The density of air is about 1 kilogram per meter cubed times the cross-sectional area. How much cross-sectional area do you think a person has? Like how much cross-sectional area do you think I have right now? I'm not quite 100 kilograms, but approximately. So just looking at me, what would you expect, right? I don't know, this is probably a little more than half a meter, right, by about 2 meters. So let's just say half a meter squared. Let's say meters. Okay. Okay, so this is 2,000 divided by 1. Square root of 2,000 is? Anyone know? Okay. So 30 squared is 900, right? What gives you, so 40 squared is 1,600. Okay, so let's say about 45. So it's about 45 meters per second, which is like 110 miles per hour. I think typical terminal velocities would say around 120 miles per hour. So we just estimated this is actually probably lower than 1. So that makes this a little bit bigger. This is actually a little bit larger than 1. I think it's about 1.2. And this is probably too big. Right? My cross-sectional area is probably like about 0.7 meters squared. Okay? So that means this number is actually going to be a little higher than this, probably somewhere between 55 and 60 meters per second. But that's in relatively good agreement with what you see. Now, if I change so that I'm no longer, so, right, if you want a good entry into water, right, you don't do a belly flop. Right, you do a head dive, right? You jump in with your feet. And that's the same thing as happening here. If I want to reduce my cross-sectional area, instead of being say 1 meter squared, if I just have my head and my shoulders, that total area is much, much smaller. Right? So if I just take the amount of area that's going along here as I'm doing a nosedive, right? That's probably, probably 5 or 6 times smaller in terms of cross-sectional area. And so therefore you can get a much, much higher terminal velocity. Questions? All right. So I want to give a couple of statements with this. This is not necessarily general. Wind, turbulence, and stuff like that is quite a complex thing. For example, one of the things they point out, throwing a javelin versus a baseball, you have very, very different behavior for those two types of things. And so this is just something considered for blunt objects, like tossing a baseball or a tuba going through air, or a car going cutting through cutting through wind. So all right. Now, questions? All right, let's talk about centripetal force. So we already talked about centripetal acceleration. Centripetal force is equal to mv squared over r, right? You just take that mass multiplied by v squared over r, and that is the centripetal force. So let me do a little demonstration here. I'm going to put weights on here. Okay, there's a lot of friction in this right now, but basically this spinning device is actually creating a tension in this cable, and that tension is keeping this up. Okay, what you can think about is, right, as this is spinning around, there's a tension in here, which is causing this to go in circular motion, right? If there weren't tension, if there weren't a force pulling that towards the center, it wouldn't undergo circular motion. And that tension that's being generated, the tension that's holding that in right there is also the same amount of tension that's in the string. And that also assumes that there's no friction in here, and there's definitely a lot of friction in this system. Let's see what the minimum amount let's spin it faster. We should start with theory. That would be really okay. Okay, so mv squared over r is basically the force needed to keep this going around in a circle. Now, what we talked about when we were talking about circular motion is that the radius, we have a radius vector that points out, we have a tangential velocity, and then we have a force. We'll just call it the centripetal force is always pointing towards the center for uniform circular motion. Okay, one of the examples they give in the book is have you ever been to a circus where someone got on a bicycle, rode it around, came up to the top of the loop? You've all been on a roller coaster, right? Where you've been on a loop. So let's find out. So let's try. draw something here at the top. How fast does something need to be moving in circular motion in order to stay on the top here? Let's figure it out. So what do we need? What are the forces acting on this? Okay, so we have mg. What else do we have? Which direction is the normal force? Down, right? Because the normal to the surface is now down. So we have the normal force and mg in the same direction. So when I sum up the forces, I get minus mg minus Fn is equal to what? Okay, mv squared over r, right? Okay, now one thing that's fairly important here, which direction is this pointing, this mv squared over r? So it's the what's left over, right? It's that you sum all the forces, and you get ma, right? And then ma is this v squared over r. And we know from this that this is pointed towards the center. So we have to be a little careful here to remember that this is minus v squared over r because it's pointing towards the center. And so if we want to consider the minimum velocity needed in order to maintain for this point up here, what we're going to assume is F normal is equal to 0. Because that is the minimum speed needed to where it's just about ready to leave the top. Okay? So what we're left with is mg is equal to mv squared over r, which implies that v is equal to the square root of gr. So all I did is I just canceled the m's, I brought r up, and then I took the square root. So that is the minimum velocity needed in order to be able to do this. Okay, so you'll notice that the mass doesn't matter. Does anyone want to do this? Have any volunteers? So let's assume my arm is a radius of 1 meter. My arm's not 1 meter long. It's shorter than that. But let's just assume that it's 1 meter for a moment. How fast do I need to have that spinning in order so the water does not come out? Let's just say 10 times 1, square root of 10. Let's just assume it's 3, right? So it's a little bit less than 1. So let's just say I have to have that spinning at minimum of 3 meters per second in order for it to go around. What happens if I don't? Okay. Shall I? This reminds me a little bit of SeaWorld when you're the splash. Okay, so I have to have 3 meters per second, so that's pretty fast, right? Okay, so that was probably, that was close, actually. Okay, no, I won't go any slower than that. I don't want to get wet. Yeah, perfect. Okay. So, I don't want to tempt fate, but so that kind of gives me the minimum speed at which this is spinning in order to not get wet, right? So if you were to take a camera and look at frame by frame, you could see, oh, that's, say, a little bit less than, that was going about 3 meters per second at the top there in order for it not to fall out. Okay. So the next example I'm going to do is, suppose you're getting off a ramp coming off the freeway, and you start doing one of these circular exits. And let's suppose that the circular exit is flat. Usually they're banked, right? So let's suppose it's flat, and what we want to find out is what is the fastest I can go around that before I'm in trouble. Okay? So I was looking at my Google Maps today, and I found a little on-ramp by my house that had a radius, say, of about 10 meters. Okay, so let's suppose that the radius is 10 meters, and here's the situation. I have a car, and I'm drawing it. This comes from the side. What is pulling it in? Sorry? Okay, so and what is causing it to, what gives it the centripetal force? I mean, there's something that's preventing my car from just going in a straight line, right? Friction, right? If I don't have friction between the tires and the road, there's a big problem, right? Then I'll just start going in a straight line. So the frictional force is what's coming here. And now if I look at, so this is from the side. If I look at it, what I'm going to have is I'm going to have a frictional force here. I'm going to have mg here. And I'm going to have my normal force here. Do I have anything else? Okay, let's sum the forces. Okay, so this is looking at my car, say head on, or from the back, whatever. The frictional force is going in this particular direction. So now I'm going to sum the sum of the forces in the x direction. Okay. Sum of the forces in the x direction, and I have f of x, and that's going to be equal to mv squared over r. Right, because it's undergoing centripetal. So the sum of the forces is equal to ma. Ma is circular motion, so I get mv squared over r. Okay, now what about the sum of the forces in the y direction? Sorry? Okay, so I'm going to get Fn minus mg is equal to 0. Okay, so all I did was I summed these forces in the y direction. Now let's assume that I have the coefficient of static friction is equal to 0.8. That's a reasonable thing for tires on a dry road, for example. So us is equal to 0.8. So how would I solve this? Well, this is the one that's of interest to us, right? Yeah.
Why is it static coefficient friction?
Sorry?
Why is it static friction?
It's static friction because if I lock the brakes, then I'm going to start to slide. That's kinetic friction. But static friction is this rolling friction, which is, if you look at a point on the tire relative to the road, it's static. Okay? Okay, so now, if I look at this, so I see that force of friction is equal to mu static. So this is going to be, what I want to find out is the maximum speed I can go before the static friction no longer holds, right? So I find that the force of friction is equal to μs times m times g. Okay? And so then I look at this equation up here. I see that mu s m g is equal to m v squared over r. And that's the m, so I get v squared is equal to mu s times g times r square root. Okay, so mu s is what? Right? 0.8. G is, say, 10. And R is 10 in this case. I should just put my units on this side. 10 meters per second squared. And the radius is 10 meters. And so I see that this gives me 80 meters squared per second squared. Take the square root of that, which is, it's about 9, right? (9 meters per second, which is, say, about 20 miles per hour. That's not very fast. Oh, sorry, this should be v is equal to this, not v squared. Why do you go a lot faster around corners when you're doing it than you go around these off ramps much faster than, say, 9 meters per second, right? You go much faster than 20 miles per hour. You don't slide off the road. Why? Yeah.
It's slanted.
Okay, so you get a tilt as well, right? They're banked, and the bank also does what? If I think about a bank, what does a bank do for me? Yes. Okay, so the normal force also contributes to, also has a component pointing inward. Okay, good. So let's do that example quickly. Now we're going to say, rather than having any friction, what is the speed I can go around a corner with a particular angle of the bank? Okay, so now let's suppose I'm on a bank here, and this is going around like this, right? This is, if you can imagine it, this is an off-ramp where what we're doing is we're coming around like this, okay? Now we have a car that's on an angle, and let's draw the forces again. What's the normal force? Well, now it's going to come out like this, right? We have mg. What else do we have? Sorry? We're going to ignore friction for this. We'll just ignore friction for this one. We're going to say, let's suppose I can go around the bank, and I have a particular angle. Do I have anything else? Okay, so what you can think about with the centripetal forces is when I sum up all the forces, what's left over is mv squared over r. So it would be so when I take all the forces, that's equal to mv squared over r, and that's like our ma, but now it's undergoing circular motion. Okay? So that's all we have for this particular problem. Now, the normal force is the component that's coming in like this. So let's just say we have an angle theta here. So if I take the sum of the forces in the x direction, what am I going to get? Just the normal force, right? The component of the normal force that's coming in like this, which is what? Well, maybe I should draw this diagram just a little bit bigger. Right, I have mg coming down. I have the normal force coming up. Right? And this is angle here is theta, just like this angle is theta here. So what is the component of the normal force that is in the direction of interest in terms of going around in a circle? F normal is equal to, F n sine theta, right? Okay? So what we're interested in is looking at the component that goes out like this. Right? It's small. And that's going to be equal to mv squared over r. Okay, now, what do we have in the other direction? Some of the forces in the y direction. Fn cosine theta minus mg equals 0. Right? Okay, so basically, at this point, all we do is solve for Fn, and then we can put that back up into here, and then we can solve for V. Okay, so the velocity in this particular case is just going to be the square root of gr tangent theta. Okay? So now if I have so let's suppose this is a 5-degree bank. I don't actually know it. Then we can find out what the maximum velocity on these particular things is. And then we could say, without any friction, here's how fast you could go around this particular corner. Okay, questions? Okay, I'll do one quick thing for you, which was a question that was raised last time after class. So the question was raised, if this is the theta, then, and this is, mg is coming down like this, how do you know that this is theta right here? So I have a vector coming down like this. How do I know that that is theta as well? Well, let's do a little bit of math here. Okay? So if this is coming straight down like this forms a 90-degree angle here, right? Okay? What does this form right up here? 90 minus theta. Now, if this is a right angle right here, and this is 90 minus theta, then this has to be theta. Okay? That's one way of doing it. Okay, questions?